Welcome to part 2 of our little cannon game. In this video we're going to look at aiming our cannon and having something to shoot at. I'm rotating my cannon to have a nice starting position so we can see more easily what is happening. We want our aim indicator to start at our spawn point, so we add a mesh instance as a child node. Then we rename that to aim. However, I don't want my object to be rotated automatically. I just want the position. So we drag it back to the root. And we reset our rotation, leaving our position intact. We'll be repositioning our node in code, so this is purely for the editor's benefit. Now I'm adding a plane mesh. I'm choosing a plane mesh because I need a rectangle that I can subdivide. First, I resize it. The width doesn't matter at this point, but we set the depth to something small. Now we subdivide it. 15 is probably a good number for now. The real magic is going to happen in a shader, so we create a new shader material. And we add a shader to that. Seeing this is a shader for a 3D object, we define the shader type as a spatial shader. Now we use the render mode keyword to turn off culling and make our object unshaded. The first makes sure we see our object regardless of direction. The second turns off all lighting calculations. I should have done this at the start, but I'm also saving my shader to a file so it's easy to access. We are going to create our own vertex shader. We're going to override the position of our vertex completely. We'll assign our Z coordinate to our Y so our ribbon becomes vertical and reset our X and Z. In order to position our vertices along our aim path, we need to know our starting velocity, so we'll add a uniform and assign a default so we can see what is happening. The x of our UV goes from 0 to 1 as we go from left to right on our original plane, so we're going to use that for our progression of time. We multiply that with our velocity and add it to our starting point. We immediately see that our ribbon now follows our linear path based on our velocity. I'm adjusting the values to something a little more representative. Our cannonball is subject to gravity, so let's add a uniform for that and give it an appropriate default. We again use our x-coordinate of the UV as our progression of time, but as gravity compounds, we need to take the square and multiply it by our gravity. Then we subtract that from the y of our vertex. Look at that, we have an arch. We don't want a solid line, however, so let's add a fragment shader as well. We take the modulus of 1 of the x of our UV coordinate. This will divide our value by 1 and return the remainder, giving us a value between 0 and 1. If the value is bigger than 0.5, we discard the fragment. Now we see that half our arch has disappeared. That's not good enough, so we'll add a new uniform that allows us to scale our value. We set this to 20 to create 20 slices. Now we multiply our UV and voila, we've got a dotted line. We want our line to be animated, and a really simple way of doing this is adding time to it. Time is a variable that increases as time goes by. That is way too slow and going in the wrong direction. So let's add another uniform to scale this and subtract instead of add our time. That's a bit too fast, so let's lower it to something better. We only want our aim ribbon to be visible in the editor and when we're actually aiming. So we hide it in the ready function. We also add some code as we process our mouse movement to update the position of our aim to be in sync with our spawn point. Notice we don't copy the orientation, just the position, which is represented by the origin property of our global transform. Now we can make our object visible when the mouse is pressed, and invisible when we release the mouse. Finally, we change our rotate cannon function by moving our velocity calculation and assigning it to a variable. We then use that variable in our lookat. And we get our material from our object and set the velocity uniform to our variable multiplied by our shoot strength. Let's test this. Note that I have resized our floor and moved the camera and cannon accordingly. We can now see how we're aiming, but as you notice, we're actually shooting further than our aim indicates. I don't know if this is a bug in Godot or whether my math is faulty, but it looks like our gravity is only half of what it is supposed to be, so we'll adjust that in our shader. That looks much better. Our cannonball now matches our aim ribbon. Time to add something to shoot at. We'll start by adding a spatial node as a container for all the elements we can knock over. So let's create our first wall element. As before, we start with a rigid body. And we move it up a little. Then we add a mesh instance and add a cube mesh. Let's make it a little smaller. Now we need a material. Again, I've prepared one earlier. We also add a collision shape to match. And let's rename it to block. We'll save this to its own scene so we can reuse it. Use Ctrl D to duplicate the node so we get a second block. And move it a bit to the right. I'm not dragging it because I want the position to be pretty precise. We'll duplicate it again, and this time we move it in the middle. Then up, and then we rotate it. It is very important that the objects do not overlap but fit snugly together. I'm still not happy with the material. It's scrunched up because the UV unwrapping assumes an equal-sided cube. One way to solve this issue is to use triplanar mapping. We'll need to reset the scale. That does look better. Let's edit our subscene. I want to tweak our rigid body and give it a bigger weight. This will prevent our cannonball from just plowing through our wall unless it has some speed. Now we can shoot at the walls and they tumble over. We want the walls to take damage and then give us a score when they break. Before we can do that, we need a way to display this score to the user. For that, we are going to add a canvas layer as a container for our 2D UI. We'll save this into its own subscene. We'll add a label to our UI, which we'll use to display our score. I'm assigning a custom font to this that I have set up before. We'll assign some default text to our label. We start with a score of 0. I'm moving this slightly away from the corner to get a bit of margin. Now we add a script to our UI node. We start by defining a variable that will contain our score. Next, we create a function that can be called to increase our score. Yes, I am adding score to itself. We will fix that up in a bit. We then update our label's text to reflect the new score. While Godot will allow us to receive signals when objects collide, we don't get a lot of info about this collision. Because our damage should be relative to how hard objects hit each other, we're going to use the velocity of our objects to determine this. However, the linear velocity of an object will already be adjusted based on the result of the impact, so we're going to track it ourselves. As we need this for various objects, we're going to create a script that we will reuse a few times. Be sure to extend rigid body. We'll add a variable that contains the last velocity we calculated, and one that tracks our last known position. Finally, we need a variable that allows us to skip some logic on the first process update. In our process update, we check if this is the first time we run it. If so, we set first to false. Else, we'll update our velocity by subtracting our last known position from our current position and dividing this by our delta to get a velocity by seconds. Now we update our last known position to our current position. We open up our cannonball scene and add our script to our cannonball. Next, we open up our block scene, but this time we choose to extend our velocity script because we need to perform additional logic here. I'm only selecting our current script to easily populate our inherits field. I also named this more generic, as we'll be using this for any object that can take damage. To save performance, rigid bodies only receive signals when they collide with other objects if contact monitoring is turned on. You have to realize that any collision is reported, including when an object is resting on the ground as it is colliding with the ground. You also need to set the contact report to the number of collisions you want to receive. We want them all, and while it's only likely to have 2 or 3, we'll set it to 10. Now we can hook up our body entered signal, which is fired when an object starts colliding with our object. We'll add a new variable to record how much damage we've done to this object. We need access to our other object's velocity, so we'll add a method to our base script that returns this value. We check if the body we are colliding with has our get method. This rules out any objects that we don't want to report, such as the ground. We subtract the velocity of the object that hits us from our velocity. Then we take the length of that vector as our strength. This is by no way accurate, as that would require knowing where we hit and at what angle. But it's good enough for our needs. I'm adding a print message so we can see what the result is. Let's test what we have so far. We immediately see in our log that all our objects are hitting each other with 0 strength. That is because our blocks are all resting on each other. When we shoot our cannonball, we see loads of collisions happening. Perfect. Zooming out a bit, we see our complete log. We see how our objects at rest have their initial collisions. Then, interestingly enough, we see our horizontal block hitting the front block first and our cannonball next. These actions actually are handled at the same time as the ball hits block 1, which hits block 3, carrying a fraction of the original force into block 3. It's just an artifact of the physics engine that the order of reporting this may be different than you expect. What is important here is that the impact of our cannonball was huge, while the resulting impacts later on are much smaller. Let's make use of that. First, we're going to declare a variable that holds the minimum strength value we'll react to. We'll only react to a collision where our strength is above this value. Next, we define a variable that holds a factor with which we'll multiply our strength to get a damage value. Now we subtract our threshold from our strength and multiply that by our factor. This then gets added to our total damage. We'll again print out this value so we can diagnose what is going on. Let's test it again. Now we see that we're only getting output if we're actually hitting our blocks. In our log, we can see the initial impact of our cannonball doing some serious damage to block 1, but the rest of the blocks getting some minor residual damage from the subsequent collapse of our structure. We're going to add a score when we crack the block, and again when we break the block. We add an export variable that determines the damage it takes to crack the block. And we add an export variable that determines the damage it takes to break the block. Finally, we add an export variable for the score we get. With 50 per action, we can score a total of 100 points for breaking a block. We'll be sending out a signal when we score. We add a temporary variable to track how much we score during this collision. We'll record what our damage was before we add our new damage. Now we check if we've exceeded our crack threshold, and if so, we add our score. If our damage passes the break threshold, we score a second time. We'll do something nice to actually break the block in the next video. For now, we just queue free our block so it will disappear. I am also disabling the collision shape to make sure we don't get any more collisions before our block is freed. If we have scored, we emit our scored signal. Now we could go past every block and hook up our signal, but seeing we'll be adding more blocks soon, that is easy to forget. Instead, we're going to do this in code. This is why we placed all our blocks as children of our elements node. For this, we need a script on our root node. Here in our ready function, we are going to loop through all children of our elements node. We simply connect our scored signal directly to our addScore function on our UI. All that is left is to fix that mistake I made in this function. And there we have it. Our score nicely increases as we hit things, and one of our blocks even disappeared when we broke it. In the next video, we're going to make scoring more visible and actually break our blocks. Then we'll add some explosions. If you found this video useful, please consider leaving a like. See you next time!